Hello everyone, this is Anthony from the Software Engineering Lab at KAIST. Today I'll be presenting a technical research paper for the Asia Pacific Software Engineering Conference 2021 titled Metamorphic Testing for Reliability in System of Systems. The outline of today's talk is as follows. This is the introduction. Testing in System of Systems. System of system refers to a class of systems comprised of independent constituent systems interacting with one another to form a larger system, thus resulting in a common goal being achieved through the set of interactions between CSs. CSs themselves are complex systems, and this results in an SOS having a large and possibly unbounded state space. This makes it difficult to generate test oracles for the testing of SOS. Suppose we want to test an SOS. We need to generate a large enough set of test cases for the large input space. The problem of determining the correct output from non-deterministic results is known as the test oracle problem. How then can we deal with the oracle problem in System of Systems? Metamorphic testing. Metamorphic testing is an area of software testing that aims to ease the test oracle problem. In metamorphic testing, a metamorphic relation is defined for the output of the system under test. A violation of this metamorphic relation would then indicate that the system under test is faulty. Suppose we have a simple program that calculates the greatest common divisor. A simple metamorphic relation is that the order of input parameters should not influence the result. In System of Systems, the large and unbounded state space makes it difficult to determine test oracles for test cases. As such, one metamorphic relation can then act as a test oracle for many test cases. How then do we define metamorphic relations for System of Systems? Reliability in System of Systems. As an SOS system of system comprises of many complex constituent systems, it is difficult to determine what constitutes reliability for a system of system. As a baseline metric to strive for, we first use a simple general definition of reliability, where the probability that the system will produce correct outputs up to time t, provided it was producing correct outputs to start with. Why do we want to test for reliability? This is especially important in systems dealing with people and safety. Systems such as nuclear power plants need to have reliable functions. If such critical functions are unavailable, there will be an adverse effect on system-wide safety. How can we utilize metamorphic testing to test for reliability in SOS? The motivation for this paper is that it is difficult to generate test oracles due to the size and complexity of SOS. In the case of metamorphic testing in SOS, how do we go about defining metamorphic relations for testing reliability in SOS? The goal is to propose metamorphic testing to deal with the oracle problem in SOS, propose an approach of generating metamorphic relations to test for reliability, and then to determine the viability of the approach by applying derived metamorphic relations into SOS simulators. Now, a bit about the background on deriving metamorphic relation patterns. A metamorphic relation pattern, or MRP, is an abstraction that describes the characteristics of a set of possibly many metamorphic relations. One such example defined in the literature is the symmetry property, where symmetry in the domain of computing is simply the observation of which the system across different viewpoints should remain the same. A metamorphic relation input pattern, or MRIP, describes the characteristics between the source and follow-up inputs for a set of metamorphic relations. An example of an MRIP given in the literature is the change direction MRIP, where it is simply the existence of a direction element in the source input, which can be manipulated to form the follow-up input. We will be extending the above methodology of identifying a metasystem's characteristic and then using it to derive metamorphic relation patterns, relation input patterns, and concrete metamorphic relations. Now for the overall approach. Firstly, for a given SOS, we identify a reliability metric. Since Nielsen has already defined 8 dimensions of SOS, we can make use of them to guide our process of defining metamorphic relations. The defined metamorphic relations need to test for both aspects of the relation pattern as well as reliability. Following that, We then derive metamorphic relation input patterns, which tells us how inputs can be transformed between the test cases. This is an example of how a relation input pattern transforms test cases. Here we have a given definition for a relation input pattern called alter set, where the set of participating constituent systems as a source input can be increased or decreased in order to construct the follow-up input. So here we have the source inputs, which are simply the participating constituent systems in a system of systems. The follow-up input can then be constructed simply by just manipulating the number of participating CSS as seen in the diagram. Next, we give some generic definitions of metamorphic relations and relation input patterns for system of systems. The first is the metamorphic relation consistent behavior, where we want to test for consistent emergent behavior across different viewpoints of the SOS. The next metamorphic relation is degraded performance, where we simply want to compare performance between the base state and the degraded state of the system of system. The next definition is the relation input pattern alter set, which tells us that the set of participating constituent systems as a source input can be increased or decreased in order to construct the follow-up input. Finally, the last relation input pattern called alter state tells us that the state of participating constituent systems as a source input can be modified during runtime in order to construct the follow-up input. Please refer to the paper for full definitions. Now for the approach. For the metamorphic relation consistent behavior, we want to test for consistent reliable emergent behavior on two SOS simulators. The first SOS simulator, called the MCIR SOS, simulates constituent systems working together in a mass casualty incident to achieve the goal of rescuing patients. The next SOS, called the Smart Grid SOS, simulates constituent system interaction in a smart grid. Using the above generic metamorphic relation consistent behavior, we derive three additional metamorphic relations. The first one is consistent power regulation, where the smart grid should regulate power generation against power demand across different system viewpoints. The next one is the consistent reliability threshold, where in the event of emergent behavior causing constituent system failure, but not total absolute failure of the entire system, the smart grid should still stay within the predefined threshold of reliability in terms of reliability metrics. The consistent emergency response is that the mass casualty incident response SOS should exhibit consistent behavior, showing the coordinated response of saving of patients across different system viewpoints. Please refer to the paper for full details. For the next generic metamorphic relation, called degraded performance, we simply want to compare performance between the base state and the degraded state of the system of systems, where we observe impact caused by failure modes occurring in the system by measuring the performance during the failure modes against the known reliable baseline performance of the system. This is the definition where the mass casualty incident response with failure modes should perform less reliably than a fully working mass casualty incident response SOS. Negative stimulus causing drop of patient saving capabilities should be observed. We want to measure how much is performance affected by the stimulus. Again, please refer to the paper for full details. Now for a brief example. As mentioned earlier, one of the earlier defined metamorphic relation called consistent power regulation. This is how the inputs are for the metamorphic relation. The inputs are the number of CSS as well as the CSS themselves. Here we see that the source test case are the constituent systems in the SOS. We can construct the follow-up test cases simply by manipulating the number of participating CSS. We then collect the output and then measure it to see if the metamorphic relation was violated. Now for evaluation. For the first metamorphic relation of consistent power regulation, we saw that by simply manipulating the number of constituents as test inputs for each run, We found that the larger number of participating CSS resulted in runtime exceptions. This was caused by functions accessing incomplete data structure of agents. We found that the metamorphic relation was violated with a probability of 0.4 of test cases. For the next metamorphic relation, consistent reliability threshold, we saw that the smaller input range of test cases seemed to result in lower passing rate for the metamorphic relation. This was obvious because lesser number of non-failed generators to provide backup power. However, the relation assumes that consumers would still get power from other non-failed nearest sources like battery storage or other generators. So why were these consumers not receiving their power? Was this due to a faulty power routing algorithm? We found that the metamorphic relation was violated with a probability of 0.4 of test cases. As you can see here, the power routing algorithm was not properly routing power. For the next metamorphic relation, consistent emergency response, using small hospital and bridgehead constituent system values resulted in index out of bounds exception. We discovered that the simulator expected at least 4 and only simulates 4 of these CS agents. We found that in this case, the metamorphic relation was only violated with a probability of 0.09 of test. Finally, for the degraded emergency response metamorphic relation, here we can see the baseline performance where all patients were saved in 900 frames, with each patient taking 9 frames to save. This is the baseline performance. This graph tells us the number of patients saved. This graph tells us how long it took to save each patient. For the baseline performance, as mentioned earlier, they were all saved in 900 frames. So, when we decrease the speed of the ambulance constituent systems by 5, referred to by this part here, the results were more or less the same. When we decrease the speed of the firefighters by 5, we see an increased drop of performance where not all patients were saved. Furthermore, when we decrease the speed by 10, we can see that the performance of the firefighter was 2.7 times slower than the baseline speed at saving patients, referred to by this part of the graph here, and where it took longer than or more than 1,500 frames to save the patients. The worst case scenario, as mentioned earlier, was that it affected performance by 2.7 times. Finally, on to the discussion and conclusion. For our research question evaluation, wanted to see how well does metamorphic testing handle the oracle problem in system of systems. From the 4 defined metamorphic relations, we generated hundreds of test cases without having to separately define a test oracle for each test case. We were able to apply the metamorphic relations to 2 systems of systems, where each system of systems made up of multiple constituent systems having its own complex state. The next research question was how useful is our generated metamorphic relations? Can our generated metamorphic relations expose any faults in the underlying systems? For the metamorphic relation, MRSG1 and 2, and MRMC1 expose underlying faults in both systems under test. The underlying faults include runtime exceptions in both systems under test, as well as a specific algorithm problem in the smart grid system of systems. The metamorphic relation MCI2 showed that certain design considerations could unknowingly affect performance. Finally, our conclusion. We proposed the application of metamorphic testing in system of systems to handle the oracle problem. We proposed an approach for metamorphic testing in system of systems and applied it to system of systems and showed that it was able to expose underlying faults in the system under test. The limitations are the derived metamorphic relation quality was limited by our area of focus. It limits the metamorphic relations to this area and may not be able to cover inputs not within these areas. The applicability of the approach where the approach will only apply to 2 system of system domains. Our future work is to apply our approach to more system of system domains and test for other type of quality metric. Thank you for your time.